So, we're talking about the map pattern, simplest parallel design pattern. There are n tasks, they're all the same, they're all independent, they don't have any side effects. So if we execute this in parallel, we can potentially run that up to order 1. And remember, the span is a theoretical measure. It's not how long the thing actually takes. The span is how long it would take if you had a limited number of processes. So that's if you could exploit parallelism responses algorithmically possible. So in practice, you might only have 3 processes available, which means you're actually going to run 3 of these ones. Then running it through. And you have to do a different calculation to find out how much time it's going to take on your particular machine. And remember, these orders are written as thetas. They're big thetas rather than big others. Theta is not the close fusion of those. That means we know for certain it is going to be this order. It's both a best case and a worst case. And best case and worst case are the same. Big O is just talking about the worst case. So, in theory, the map is really simple. We're just going to launch n copies of that task. And you think they're going to run like this. You think you're going to launch 5 copies and they're all going to appear as work items and run parallel. That's not what usually happens in practice. So, but first of all, for non-trivial algorithms, different executions may take different lengths of time. So this kernel, for example, is a divide kernel. Okay? Divide is a bit more complicated. You have to check if the number is 0. We need to avoid divide by 0. So you notice this kernel now has a branch in it. That means different executions of the kernel may take different lengths of time. And that's where the different notions of complexity come in. So we're talking about the best case complexity, which would be big O, the worst case complexity, which would be big O. We have detail when they're both there. So first of all, different executions may take different lengths of time. So these executions are the ones where the branch has gone the other way. We've noticed that a division by 0 has been requested, and we've decided we're just not going to. Longer executions, everything looks okay, and so we proceed and we actually carry out the division. So, secondly, you're not guaranteed that the kernel will launch at the same time. When you specify that, there's no promise about how the execution is going to be done. That's the point of the map. We're specifying the work to be done rather than how it's going to get executed. So in practice, you may find different executions of the kernel will launch at different times. And here you've got a mixture of different launch times and different launch durations. Okay, creating a much more complex structure and the theoretical idea of the map pattern would lead you to do. So you're going to be writing some maps in the workshop. Some of you may have already started writing some maps in the workshop. One of the main tricks or techniques around map programming is to convert sequences of maps into maps of sequences to make your programs run faster. So let's say you've got a whole sequence of numerical operations. For example, you want to do some multiplying. You might say run a map to multiply all the elements of A with B and store it in C. And then you might want to do some adding, take all the elements of C and add them to B. And then you might want to do something else. And you see, this is a sequence of maps. Okay? Specifying one map execution. You can often make this go faster on many systems, including OpenCL, by converting that structure to a map of sequences. Okay? So what we've done here is we've defined a single function that does all of that arithmetic on a single data item. So we've done some multiplying, we've done some adding, we've done something else. Maybe this is going to be a sigmoid function, and the thing would look like a neural network. is what most people are using parallel programming for right now. So this structure is probably going to run faster on these system because all the overheads to do with initializing a map and sending stuff to and from the GPU and curating the parallel execution process only has to be done once. Yeah? Usually once you've done those overheads, actually running the kernel is the easy and fast part. Especially if you're working with relatively small kernels, as in student workshops. So a simple programming trick. Look for any sequences of match you have. What's the downside of doing this? Downside? So from a software engineering point of view, this is not so great. From a software engineering point of view, you might like having a collection of nice, simple, reusable functions like multiplying and adding and sigmoiding. So these are the kinds of functions you'd like to put in a library. A library like PyTorch, for example, is going to do exactly that. So there's a bit of tension here between usability style software engineering and pure performance. If you write this function, this is going to be a very customized function. This is a function that does a specific combination of adding and multiplying and sigmoid functions, and it only does one thing. It's going to be hard to reuse that for anything else, but if you've got a nice library of primitives like adding and multiplying, that can be much more reusable. So sometimes you are going to have to trade this off, as with everything in software engineering. There's a trade-off between beauty and reusability and that kind of niceness and pure performance optimization, which is another kind of niceness. A couple of other real-life factors you will encounter in OpenCL and in other systems. What happens when n becomes large? In particular, if it becomes larger than the number of processes available. So to some extent, CL will help you with this. It will automate some of this process. Let's say you have a GPU with 10,000 processes. Compute units available, processing elements. Say 10,000 processing elements. Remember, those things are grouped into CUs. CL likes to have full compute units. It likes all the jobs to run in parallel on a single compute unit. That gets you nice SIMD style execution processing element. If you get bigger than a compute unit, CL will automatically take some of your jobs and shove them on another compute unit. Those are called work groups. Yeah? Let's say you can run 1,000 jobs on a single compute unit. If you put in 4,000 jobs, CL will automatically partition, put it into 4 work groups and assign each work group its support. What happens if the data gets even bigger? If you have more work than you have available compute units. So in that case, CL will help you again. It will start to serialize work. So if you only have 4 compute units, for example, and you've got enough work to fill a compute unit, it's going to send it to the 4 available compute units to do 4 copies, and then after that, it will send another 4 to the same one. So you can see if you run out of parallelism, it's going to start serializing. You'll see very different time requirements than your theoretical pattern. What if your data gets even larger? So this probably isn't the case for processing an image. This is more what happens if you're doing data science. Well, what if you've got a petabyte of data and you want all that processing on a GPU? You can reach scales where you can't even fit all the data on the GPU. The GPU memory is quite large. You might have a couple of gigabytes on your NVIDIA GPU. And most of that is sitting here in this shared device memory. What if the data you want to process is much larger than what is available? So in cases like that, CL isn't going to help you anymore. Okay, CL will max out and it will throw a error message saying, no, I can't handle this much data. So at that point, it becomes your problem as a programmer to figure out how to handle it. Basically, that's going to involve you cutting up the data into sensible size pieces. You might cut up the data and chop it into 12 gigabytes at a time, send each of those chunks to a GPU, and CL isn't going to help you on a scale bigger. Even a really simple pattern like a map leads to a certain amount of complexity when you start thinking about how the thing actually gets executed. We can generalize the idea of a map in a couple of directions. One of these directions is called scatter or gather. Scatter and gather are two closely related patterns that I usually discuss. In the scatter pattern, you've got a bunch of input data. Each input item is going to get an identifier, and that identifier corresponds to a job number, as in corresponding to a process that actually gets it. So in this case, we've got 6 inputs. We are going to launch 6 tasks in parallel. Each of those tasks gets associated with one of the inputs. Okay? The difference from a map is that each task can decide where it is going to store its output. So in a map pattern, input number 1 will get stored in output, input 2 will get stored in output. In a scatter pattern, task starts at a fixed location from the input, but it decides, and making that decision could be part of its computation process, it's going to decide where to store the output. Okay? So you see there's regularity on the input. The output looks more random, so we call that scattering. It's like taking an ordered bag of seeds and scattering them on the ground. Gather pattern the other way around. In a gather pattern, it's each output location that has an identifier. Okay, so that the output is nice and regular. Every element here corresponds to a task that gets launched that has an integer identifier. So you're going to get exactly 6 tasks launched in a row here. And it's up to those tasks again to decide, in this case, to decide where they're going to take gather pattern, each task decides which element in the input am I going to consult. Yeah. Scattering is throwing stuff out, and gathering is bringing stuff back together. In the scatter, things are getting less organized. In the gather, things are becoming more. So here's an example in OpenCL of how to do that. Here's a kernel. Every kernel has an identifier. In this case, though, we're not writing directly to the identifier's location. Yeah? If this was a map, we'd say C of ID equals A of ID. In this case, we're going to say C of some function of the ID. And this function is something that we could be calculating. Now, this is a little harder than a map to get right. The gather pattern is straightforward. In gather, you can see every task is going to execute independently. There's no interaction between tasks. Can you see, looking at the screen, can you see what might go wrong in a scattered pattern? There's a particular failure case that this is exposing us to now. Remember last week we talked about things that can go wrong in arbitrary task-based programming. Right, so what could go wrong in scatter is that 2 input items might decide to try and write to the same output location. So for example here, look, you see this D? Both tasks 0, 1, 2, 3 and task 4. Task 3 and 4 have been launched as input jobs corresponding to input data items. They've both decided to go and write at location 2, yeah? 0, 1, 2. And at that point, the output is now undefined. You have a race condition Yeah? Race condition means two processes in parallel, both trying to hit on the same resource, and you have no idea what order that's going to happen. And whoever runs second is going to get to overwrite whoever ran first. Yeah? That's exactly the kind of mess that these design patterns are intended to protect us from. So, to make scatter into a formal, usable pattern, it's not enough just to say we're going to launch 6 jobs and have each job go right and next. There has to be this extra condition. We're only going to define implementing the scatter pattern if this particular condition is met. The condition is we've got to prove that no 2 tasks are going to write to the same location. If you can't prove that to yourself or to someone else, then you're not allowed to call it a scatter pattern. Okay? This is really important because the point of a pattern is to try and create this protected, nice version of your programming world where everything behaves and keep it separate from all the styles of bad programming that are going to get you into a mess. And this is one of the lines you cross. If you can't make this proof, then you're opening yourself to that kind of bug of getting into a race condition. Okay? So the gather pattern is easier. Okay? Gather is always going to work, but scatter has this particular failure case. And if you try to implement the scatter pattern, you have to know about that, and you have to come up with an explanation that what you're doing really is a scatter pattern. Okay? That means proving that you're not going to get into one of these race conditions. But that's a little bit like what we had to do before we had design patterns. You had to do this for every parallel program. You had to go through that and make these proofs to show that it was never going to get into a mess. And that was generally hard work. So you have a little bit of hard work to do here, but because it's constrained within the idea of the pattern, it's going to be a bit easier. You've only got to make that proof for this one small part of what we're doing, and then you can say the rest is just a pattern, so everything is now going to work. And that might give you a little bit of insight into how some of the other patterns go. Sometimes there is unavoidable complexity when tasks have to interact, but the general idea of the patterns is we're going to try and capture it and control it. Where there is unavoidable mess, we're going to put the mess in a little box and say, this is where it is, this is where it is. Okay, so the stencil pattern is another simple generalization of the idea of a map. It looks like this. And in various subjects, it might be known as a filter or a convolution. The idea is that each task is going to look at a region of data input, usually a spatially contiguous region, having a bunch of points that are all around each other. Each task is going to look at an input region. It's going to do something with all the points in that region, and it's going to write a single output. Again, as with map, we have the constraint that there is no other communication between the tasks. Okay, so no side effects are on node, and no communication, no messages are back and forth between the tasks. So this again should have nice properties. Okay, you're allowed to read multiple data items. Can you see these 2 tasks, for example? These 2 tasks are both reading some of the same data inputs. Yeah? But they're not interacting in any way. The inputs are all fixed in advance. Once you give the system the inputs, nothing this task can do can interfere with what the next task is doing. So again, that's the idea of the pattern, is to try and enforce sanity and cleanliness and keeping things separated from each other. For example, stencils are often used for averaging things, or sometimes this is known as blurring or convolving things. Let's say we have some input data that looks like this, and we would like to do some averaging Okay? So in this case, we're saying each output is going to become the mean of the 3 inputs around it. Okay? So here we've got 2 instead of 3, and the mean of those should be 4, which is getting rid of 20. Here's an OpenCL implementation of that. We go and get our task ID, and we're writing the output. The output ID is the same as our task ID, but you can see the inputs we refer to can be different from the task ID. So it's multiple inputs that are densely together. What do you notice about the input and the output in this case that's different from different lengths? Okay, when you do this kind of spatial averaging, so very well-known problem in signal processing data science. If you do any sort of spatial averaging or blurring or filtering, you will typically end up with an output that is a little bit shorter than your input. Because the nature of averaging is that it's condensing information down. And this can generally be annoying and painful, but it's something you have to deal with. A nice property of the map is that the output structure looks exactly like the input structure. In particular, that means you can chain many maps together in a sequence. You can't do that with stencils unless you come up with some scheme for dealing with using the objects. In particular, if you run a input array through a sequence of stencils, it's going to end up getting smaller and smaller and smaller until eventually you've only got one bit. So sometimes that's okay. Other times you have to come up with workaround, like you might decide to write a 0 in both ends of it, and you might decide to pick whatever numbers on the end, blur it to the edges, and back up to the edges. There's always going to be what are called boundary conditions, figuring out what is another common technique is to assume that the input array is actually a loop, okay, that is written on a circular piece of paper. And so if you wanted to calculate the value here, you can take the average of, say, these 2 points and the one from the other end. That's sometimes called a circular calculation. That's a one-dimensional version of this stencil. We can take the same idea in higher dimensions. As you go to higher dimensions, there are more alternative ways of setting this up. So let's think about a 2D stencil. So this is the kind of thing you would do in image processing, for example. You want to calculate some value to go here in this pixel as a function of neighboring pixels. And here's 3 common ways of setting up a 2D stencil. This is a 4-point version. You can see we're not taking value from the center cell, we're taking values from the 4 neighbors on the cell. Or you might decide to include the center cell as well. I'll give you a Python example. Or you might decide to include a square window around the center cell or excluding the center cell. When you go to 3D, there's even more options. So here's the equivalent of a 4 versus 5-point cell. You can have 6 or 7 points, depending on how many neighbors you want to include, and do you want to include the center cell. As the thing gets bigger, there's now loads of options. You could decide, do you want to take a massive around the center? Do you just want to take lines coming out from the center? Or you might decide to have a kind of cube structure in the middle with some star-like features coming out to the edges. And in some cases, the application you're working on will give you suggestions for how this should be done. So this is common, for example, in weather modeling. You might have seen the recent GenCast weather models. They've been making a lot of headlines for predicting the weather better than physics-based models in neural networks. And in GenCast, they take the atmosphere as a 3-dimensional space and they cut it into squares just like this. And you've got to make these stenciling decisions for how the squares going to interact. So here are some more applications of stencil patterns. If you do any work in audio, speech processing, or music processing, if you are interested in making digital effects like these guitar pedals, for example, These three particular audio effects are all direct implementations of stencils, okay? EQ, chorus, and reverb. They're actually all the same effect, just running on different timescale. And they're all cases of a one-dimensional stencil pattern. So you can take a sound wave. Your sound wave comes as a sequence of data points, call it xn. You're going to delay it several times. The symbol z to the -1 means delay. So you've made several lagged versions of your signal, and then you're going to weight them, and then you're going to add them to get a classic stenciling pattern. It's just like this. You've got a series of numbers coming in, sound waves, and you're going to do some sort of averaging operator so that the output at time t depends on some of the inputs going up to t. When I worked in speech, we did some studies of this. We spent a lot of time recording people in different environments and looking at the acoustic properties of the filters created by those environments. What you find in most environments looks a bit like this. The sound you hear contains a copy of the original source. You get a bundle of what are called early reflections. So these are the immediate waves that come back. When my voice bounces off this wall and lands in your ear, that's an early reflection. But then beyond that, you get this much longer sound, where the sound has bounced off one wall and then another wall, and potentially bounced many times, and it creates a tail of reverberation like this. So you could use a stencil pattern to create this shape. Okay? If you want to simulate the reverberation, you can say my output at this time is going to be whatever I'm hearing now plus weighted versions of several previous that have time to reflect around the room. Make those reverbs really close together. You will start perceiving them as a single sound rather than many reverberated copies. That's called the chorus effect. That's how you turn a single musician into what sounds like a small group of musicians all playing something. Or if you consider these effects on a really local level, it becomes we're looking at the difference between the bass frequencies and the treble frequencies, and the same kind of filters can be used to implement a graphic EQ. Now this is an EQ that lets you turn up and down. So these are really all the same effects, just running on very short, medium, and long timescales. But you can now implement on GPU. This is probably how your audio workstation is working together with GPU. In vision, graphics, image processing, you will find a lot of 2D stencil patterns. So many visual effects are calculated as convolutions, such as a blurring effect. Let's say you want to take your nice clean image and apply some blur. In particular, you might want to do this to the background of your image to simulate focus, or to bring the viewer's attention to certain points of the image that are in focus. So the blurring effect is going to do a 2D stencil. You're going to take each pixel, and you're going to look at some window of the pixels around it, and you're going to set that pixel to a weighted average of all the pixels around it. Again, because this is a stencil pattern, we have these guarantees in place. We have the guarantee that we can calculate each pixel independent of the others. We can specify it, like in a map, as a set of work to be done in whatever order, and we know that we'll always get the same output without any interaction between these processes. And nowadays everyone wants to build neural networks for everything. You will find exactly the same structure inside what are called CNNs, convolutional neural networks. Often used for image processing. The idea is the same, just like in a blur filter. You're going to take small windows around each pixel. We're going to make a weighted sum of the neighbors. In neural net, you're then going to pass it through another function, like a non-reducible function. That's going to give you the input to the next layer of the network. And in CNNs, you can end up with higher dimension structures than 2D. You might start off with a 2D image, But you might say for each window here, you might actually compute 10 different neural processes on it. Okay, 10 different neurons all look at the same number in different ways and then compute different data. So you might end up with three-dimensional or even higher dimensions, which in this context is known as a tensor. Okay? A tensor is a higher dimensional version of a vector or matrix. And you're going to propagate these stencils through many layers of the network until you get to a few neurons at the top that tell you whether you're looking at a picture of a kitten or a puppy. Does anyone here use PyTorch at all? If any of you use PyTorch, it's a Python library. It's intended for building neural networks. So what PyTorch really is a large collection of OpenCL or similar functions, things that do addition and multiplication and calculate and separate functions. Many people will use a proprietary implementation of PyTorch, CUDA, but there is an OpenCL implementation of PyTorch. If you're interested to see what CL can do in the real world, I suggest you have a look at it. It's all open source, and you'll see a whole bunch of OpenCL kernels, like the ones you're writing in the workshops. And each of those kernels implements one ingredient of what you need to make these neural networks. And they're provided through PyTorch. It's an user-facing API. So the last pattern we'll talk about today is called reduce. This one is a little different. We'll introduce it using an example. Let's say you want to calculate the sum of a bunch of numbers. Okay, here's an input array. I just want to add them all together. If you do this in series, you would probably go about it like this. This is called a cumulative style architecture. This is an inherently serial program, right? We've created a variable called sum. Every time we go around the loop, we're going to increment that variable. So you'll notice this is not a map. Okay, this is a true loop, this is a true dependent loop, and it does matter what order you run your iterations. Every iteration is hit on this shared piece of memory. You don't have that property of independence. So you can see if there are n items, this serial program is going to take order n time to do the computation. Right? We've got a loop round and do addition for every item. And you can see that the sum at each point in time depends on the current data item, but it depends on the value computed before it. So it's not completely obvious how we can parallelize this. Yeah? So this is a little harder than a map to put into a parallel pattern. So it's possible to do it. Like this. So imagine you have a class of students, and we're going to do this addition as a team problem, right? We're going to give everyone one of these numbers. We're going to say, get together with the person sitting next to you and add your numbers together. And when you've done that, your group is going to pass its numbers to the group sitting next to you, and they're going to add whatever they got before to what you've given them. They're going to pass it to the group sitting next to them, and eventually it all comes down to the middle, and the student at the front does the final addition. Now this is a very different algorithm from the serial version. Yeah? It's not a direct translation. The reason this works for addition is due to a mathematical property called associativity. One bit of associativity? Associativity is this property. It means if you've got A plus B plus C, it's the same as A plus B plus C. It means you can move the position of the bracket. So associativity doesn't just apply to addition, it applies to many but not all mathematical functions. So for example, you can also do this with multiplication. If you wanted to multiply all these numbers together, you could use the same trick, because multiplication is, if you want to find the maximum value of the numbers, max and min are associative functions. You can set up the mean. Mean is a form of average. You can set up the mean as an associative computation. some functions don't have the associative property, in particular subtraction and division. Okay? It's not really clear what it would mean to subtract all these numbers from each other, because you have to specify the divide them. So you notice multiplication and division are very different kinds of operators from subtraction and division. In the sense that subtraction and division are directional, in the way that addition and multiplication are not. But formally, if you have any operator that is associative, you can consider it to be a combiner function. So a combiner function is just an associative function that is being used as part of the reduce pattern. So we can consider the complexity. We've gone from an order n algorithm in series to something looking like this. This is going to give us order log n. Hopefully you can see why that's the case. It's to do with power 2. This is a very nice speed that we get in the reduce pattern. And you'll find reduce becomes an ingredient of many other design patterns. So it's not only useful to add these, you can many other mathematical operators. And if you can show that associativity property is there, that tells you you're probably going to be able to accelerate from order n to order log n. Okay, so this was a quick tour through some basic design patterns. Remember, the point of these patterns is to make your life easier. If you don't think in terms of patterns, you'll end up in this arbitrary task parallelism, and you'll end up with a big mess because you'll have multiple tasks all interacting with each other. In particular, trying to communicate and to share resources, and you'll end up in problems of race conditions, and you'll end up in deadlock. If you make use of the patterns, you can work in a much safer, more controlled environment where things work. And we had a little hint in the scatter pattern, but in some cases, the problems are still going to be there. Scatter has this one particular case where a race condition is there. And the way we get around that is we define the pattern as excluding the cases. If you're going to use a pattern that has a change requirement, it's still a problem with the program until the conditions are satisfied, then everything can go. So today we've looked at map. That's the basic data parallel pattern. We've looked at scatter gather and stencil extensions of map. We've looked at reduce. Next week we'll introduce a bit more theory of communicating and interaction between processes. The week after we'll look at some more advanced patterns that rely on some more see you guys in the workshop. It's going to be nice and please make sure to read a chapter of something that we're interested in, how Python that's together.
There's a back entrance into the building.